I would like to first present our speaker, Dr. Karthik Mukkavilli. He is Group Head of AI and Principal Scientist at Mercuria, an energy trading firm. He works with data science and computational methods to address environmental and societal challenges for global scale impact. So please give a warm welcome.
Thanks, Sarah. Really glad to be here. I'll be talking about this broader topic of AI for complex systems, the advancements, challenges, and opportunities as I see them in the space. So advance number one, which everyone should be familiar with, working at the intersection of AI and climate, is we have these surrogates or emulators. These emulators work quite well on the data that they've been trained on, which happens to be mostly Era 5 at 25 square kilometer or so resolution in this community. They've been, within that space, they tend to be state-of-the-art and are beating some of the baselines, but there's still a long way to go on the spatial and temporal scale for it to cover the range that Earth system models provide. But there is work underway towards an Earth System Foundation model in this community. There's also been a bunch of state-of-the-art models across a smattering of different companies here. You can see from Huawei to NVIDIA to Microsoft to others have all been releasing these models. Advance number two is a paradigm around foundation modeling itself. There have been some great pieces of work in this space, essentially having a pre-trained backbone from geospatial data. This could be multispectral. It could have different levels of resolution. And essentially, once you have a pre-trained backbone, you can attach decoders to fine-tune on a specific task. So essentially, it could be generalizable at the backbone level, but it really comes down to how well it's been fine-tuned on some of the tasks. So there's still further work to go in the space. Now, another advance is around domain-specific large language models. Large language models have been trained on the internet's knowledge, essentially, and a bunch of books from everywhere that you could find. But they tend not to generalize very well, especially in enterprises like Mercuria or other companies around the world where there's a lot of internal-facing data and taxonomies and knowledge graphs which need to be ingested. So this was a project with NASA where there was an effort underway to integrate all the astrophysical Harvard sort of databases and other scientific literature to see if one could develop domain-specific large language models. And they do tend to outperform compared to a purely generalizable model. Okay, I guess I didn't count the numbers right, but another one is reinforcement learning. So in this space, obviously, reinforcement learning has now been applied towards reinforcement learning-based human feedback for tuning large language models. But an area which is underdeveloped is taking RL from simulations to lab-scale experiments. And this also tends to be sort of multi-scale phenomena. So in this project, which was published in Nature Machine Intelligence, you can see some of the work. So essentially, you have these ultrasound microbots which can be steered, and it's utilizing a model developed by Google DeepMind, Dreamer, to imagine paths, and then you can see this microbubble navigating. Obviously, this would have applications towards drug delivery and things like this. So it can go through multiple obstacles. It generalizes super fast, like once it's been pre-trained and then moved across to the lab. Now, I want to touch on the biases. in these models. So this is a challenge, right? A lot of geographical information within climate literature and earth science literature isn't really encoded very well into language models yet. So you can end up with a whole bunch of biases resulting from this based on, is it sort of London in Canada versus London in UK? How do you deal with such sort of issues, right? So obviously context helps, and LLMs are good at this, and we can resolve it. But what we did find in this work was there was a lot of inequality even within the climate literature or earth science literature itself in their focus. So in low-income regions, 100x more people needed to be affected before research happened. But potentially, an LLM could be used to resolve some of these biases, but at the same time, you would need to account for where research hasn't been done, and this comes down to like on-the-ground work to bridge these gaps. Now, an area of application, I know I'm going through multiple fields here, but I want to draw a link between complexity at different scales and across different applications. So what I'm doing right now is scaling solutions to energy markets. And energy markets face similar sort of issues related to noise in the markets and biases, and the signal-to-noise ratio isn't as good similar to biodiversity in many ways as well. So Mercuria is a leading energy trading firm. We're based out of Geneva, but in 15 different countries. We trade, we have assets and investments in renewable energy and other assets around the world. Also invest in net zero solutions. We have a 50% investment target set to low carbon, which we've already exceeded. Take our profits and put in $1 billion into low carbon solutions. And we created a 500M vehicle into biodiversity, even before the market really exists for this. So the challenges for us is, as I said, markets are noisy, so extracting meaningful signals that impact them is really difficult. And AI isn't great at this yet. Now, we don't deal in the high frequency range for trading. We deal in the low to medium frequency range, which is where it's even harder to extract signals. In addition to this, a lot of the information which can add value to us tends to be super sparse. So, and the information advantage and the asymmetry in it is what ends up enabling us to trade. So at the moment with AI, this is quite difficult to extract. And it tends to be from knowledge of the traders who themselves are sort of like the rocket scientists of what's happening within this market, right? That they're focusing on. Now, the other area of difficulty is, unlike in earth sciences and climate, which is governed by physical laws, these are human dynamics in the market, and the environment continuously shifts. So it's not like in earth science, you might model the Earth, but next moment you're on Mars, and then the following moment you're in like some other exoplanet. That's how markets are, so it's even more complicated in that sense. And this can change due to geopolitical shifts, supply chain shocks, and so forth. So yeah, I'll stop there. This is a nice plug to, there was a talk by Michael Jordan, who's my postdoc advisor, who, when he came to Mila, he spoke about if there was like an alien civilization which came to Earth and then saw what would be intelligence, right? They would observe how we transact and trade in our markets as being a sophisticated mechanism. So that inspired me to kind of get into this AI for complex system space and start seeing the relationships between climate to biodiversity to Earth system science. So I'll pause there. Thank you.